Hi, everyone. In Lesson 15, we talked about discrete probability distributions. Now, in Lesson 16, we're going to talk about the expected value of such a distribution. What happens in the long run? So, you may remember this notation here. I hope you do. Mu, this Greek letter represented population mean. But now we're going to talk about the mean of a probability distribution. This is also called the expected value of a probability distribution, denoted by E of x. E of x equals mu. They're interchangeable. The expected value of a probability distribution is the mean of that distribution. Now, the formula for this is given here. And this should remind you of this formula over here from Lesson 8. So this formula here was used to compute things like GPAs back in Lesson 8. Remember that the numerator up here, the top, summation W times X, that corresponded to a zigzag motion throughout a distribution. And on the bottom, we had the sum of the weights. Okay, so remember back in Lesson 8, let's recall this formula. This was a GPA problem back in Lesson 8. You should remember these. So remember how we computed GPA. We looked at the number of units. We looked at the corresponding grade. In particular, the grade recoded as grade points. Like, for example, an A minus was a 3.7, and so forth. And we did the zigzag. That's what this summation W times X gave us. We add products. So we wanted, as the numerator, this times this, plus this times this, plus this times this. The weight, the W value, times the X, basically the grade value. We wanted these products. We took these products and we added them together. We added these products. We added the products, W times X. And then we divided by the sum of the weights, that is the total number of units taken by this student, in this case 12 units, and we computed the GPA. So again, when we computed GPA, we did that zigzag motion, we got the numerator, and we divided by the sum of the weights, the total number of units taken by the student, 12 units here, and we got the GPA. Now over here, when we're talking about this zigzag formula for a probability distribution, what is the sum of the weights? Now the weights are probabilities. Before, weights were given by the numbers of units for the classes, 5, 4, and 3. But now for a probability distribution, the weights are probabilities. And for a probability distribution, what must be true about the sum of the weights? They have to add up to what? They have to add up to 1. So basically, we're taking the zigzag formula from Lesson 8. We know that the sum of the probabilities in a probability distribution, well, that has to be 1. So we can ignore the denominator there. And we're basically left with this formula for the expected value or mean of a probability distribution. E of x, or mu, equals summation. The weights are the probabilities. The probability of x times the x value, or you can switch these, summation x times p of x. And again, we divide by the sum of the weights, the sum of the probabilities. We would divide by the sum of the probabilities, the weights, the summation p of x. But wait a minute. For a probability distribution, the sum of these probabilities will be 1, and we can ignore all that. We can just take this. All right. Now, what's the interpretation? The expected value of x, or the mean of the distribution for x, gives the approximate long-run average per repetition if the random experiment, like rolling a die, for example, the experiment that produces the value of x, if this experiment is repeated many times. So let's say you roll a die 1,000 times, or 10,000 times, or better yet, 1,000,000 times. Then E of x will give the approximate long-run average value for x. This is the result of the law of large numbers. The idea being that the probabilities you see, which are maybe theoretical, idealized, they're the targets. The idea with the law of large numbers is that the observed relative frequencies for, say, the die faces 1, 2, 3, 4, 5, and 6, the observed relative frequencies will observe the theoretical probabilities, namely 1/6 apiece. All right. We're going to see some examples for expected value or mean of a probability distribution next.